Hello, in this video I want to show you some details on the package I wrote called Shattering. This is an R package which is available in the CRAN, the official repository of the R statistical software. This is the last version. Actually, it is still a version that I'm working on, so it's not actually the last available version, but it will be made available like really short. I would like to make it like to submit it to the official repository until this month of October 2020. Okay, so this is the description. You guys can look for this version. It will be 1.0.2, and it depends on a list of packages, as you might see over here. It depends on all those R packages that are available with the language. I want to show you this directory R, so I'm gonna go inside it and just comment a little more on the functions we have here. The first function to discuss is this one, equivalence relation. What is important about this function is that somehow we are going to connect points in a given space. That connection comes from open balls. So if you guys define, for example, a given radius, that radius will be used to connect a central point to any other point in its vicinity, its neighborhood, depending on such radius. So we're gonna build up lots of open balls to connect points respecting the topological space. If I go inside this function, you're gonna see this. Let me go up. You're gonna see there's some comments about the parameters, etc. So here, of course, I'm going to discuss some details on this function. First of all, this function receives a given input space and its class labels. So the class labels for every input we have in X. For every example we have in X. From that, I'm going to compute something here with you. Oh, this is not necessary. We're going to compute something together, which is a vector called radius. What I'm going to do at this point is this. I will select the unique classes we have inside this vector y, and I'm going to assume every possible value in that particular vector. And every time that value happens to appear in my numerical vector, I will bring those IDs to this vector. What I'm going to do with this is basically something quite interesting, which is this. I'm going to compute this function knxdist from package fnn, this package fnn, among every point we have in our X set or matrix, which is our input set, except those IDs. So I'm just removing those IDs from my set using this function setDiff, as you guys can see here. Then I will compare how distant all those points are from my points associated to those particular IDs. and I want the nearest neighbor. What is behind this comment over here? What is exactly behind this comment is I want to compute how close every point belonging to a different class is from the points belonging to a particular class C. So I take every point we have in our input space belonging, for example, to the positive class, and I want to compute how distant they are from the nearest point from the other class. If we have just two classes, of course, this is going to be, for example, the closest point belonging to the negative class, and that's why we use k equals 1 to get the closest point belonging to the other class. I'm using a KD3 algorithm to perform this, just to make, of course, this function faster. And then I subtract a very small number, just to make sure this radius is not going to be enough to connect a point belonging to a given class to a point belonging to a different class. So if this point belongs, for example, to the positive class and the others to the negative, so I don't want that particular radius to allow the connection, allow the equivalence relation. If you don't know anything about equivalence relation, try to study a little bit about topological spaces or topologies, okay? So, and in this point over here, I'm just getting the closest radius that a given point belonging, for example, to the positive class, what is the closest point belonging to the other classes or any other classes that is closer to a particular point belonging, for example, to the positive class. Why that? In that way, I have all the radius that that can be traced somehow, can be used somehow to build up open balls and building up equivalence relations among all points belonging to the same class. So my idea is I'm going to use this radius to compute the homogeneous class regions, as we discussed before. So I'm going to use those radius to understand what is the maximal open ball radius I can use to connect a given central point to any other belonging to the same class of this central point, in order to reduce my set, in order to reduce my space, in order to find how many homogeneous regions we have. Here, I get all those radius computed over here and saved in this vector, and I compute a quantile of those radius. Why that? Of course, we're going to have, for every point we have in our space, we're going to have what is the closest point to it that belongs to another class, to a different class. When I decided to add up this quantile percentage here, I'm just telling you that I'm not going to consider all those radius, but instead just a percentage of those radius. So, for example, if quantile percentage is equals, for example, to 1, this means I will use all radius. All radius. If I decided to use, for example, let's say instead of 1 could be 0.5, I will take the median value of this vector radius, and I need to consider that as the greatest distance to be analyzed. Why that? Because of course, if we have like very far distances, we could just in between a given point belonging to a class, 2 points belonging to a different class, I could just forget about those distances and disconsider those distances because they are very far. So that's a way, much more like a way of reducing the processing time of our approach. If I consider 1, I'll have the perfect and complete solution. If I use something as a fraction, like 0.1, I use 10% of those ranges to obtain some upper bound for distance. Then I will take all the ranges that are less than or equal to such a distance, and those IDs will be filtered out. How? I'll just filter out radius is going to receive radius of those IDs, X is going to receive X at those particular elements given by this vector IDs, and Y's as well. That's a way of reducing my sample and perform operations faster. If you guys don't have like a bunch of time to wait for processing some large scale data set, you can start using quantile as 10%, like 0.1, or 5%, like 0.05. And after analyzing the results, try to increase a little more. If you have time, just use 1, because that's going to produce the best solution, or the most complete solution, of course. At this point, we are going to do the following. We're going to get all those classes that happen in Y, in my set Y, and again select all those points whose class is equals to C. I will of course build up some subset over here. What I'm going to do with those subsets here, I'm going to define some IDs from sub to sub plus chunk minus 1. For example, in this function, I define by default chunk equals to 250. That means we're going to go, for example, from 1 to 1 plus 250 minus 1. That's 250, of course. So we're going to compute 250 elements, distances to be more precise, at once. Why that? Because here we compute those distances, as you can see, from those particular elements. Take a look. IDs has all those elements I am considering in my analysis of trying to reduce my space to homogeneous regions, to homogeneous class regions. So when I come up with this index elements, I'm just subselecting inside IDs the elements I will be considering my analysis instead of considering all elements. And I do the same with this. I'm computing how close those points are to X, to every element we have in X. Of course, now it's not X, the original X anymore, but of course, but a subset of X, because we are selecting just those whose radius are smaller than or equal to a given distance. Why this? Because of course, those radius are the most prone to form homogeneous class regions, whose radius is smaller than or equal to a given distance. That's why I use this as a way of making, of trying at least to make the execution faster, to make this to reduce the processing time at the end. Okay. So using those distances, what I do here is I'm going to perform some operations from the first to the last number we have in this matrix. What is inside this matrix? This matrix has all the distances that those particular elements have in comparison to any other inside X. Of course, this this subset of x. If the element, if that distance of a given row, this given row is actually the distance for the first element we have in IDs, the second, the third, the fourth, and then every time that distance is smaller than its corresponding radius, and this radius is actually the one we computed, of course, here. We selected a subset of radius. Those are the nearest neighbors belonging to different classes. From that, I take, of course, those radius to build up an appropriate open ball and saying, okay, if a point has a distance smaller than that particular distance, just get those IDs. And those IDs are going to be associated with nearest neighbors from the same class. What is my point here? Consider you guys have like 6 points in a space. 3 points belong to the positive class and they are close to each other. 3 other points belong to the negative class and they are also close to each other. And of course, positive points and negative points are far from each other. Okay, in that particular scenario, what I'm building up over here in my matrix R is something like this. Those 6 points will be like this: 1, 2, 3, 4, 5, and 6, of course. And here, 1, 2, 3, 4, 5, and 6. 1 and 1 belong, for example, to the positive class, so they are neighbors. I'm going to set value 1 in this R matrix over here, as you can see here. This is a way of building up a sparse array to contain something like this. 1 and 1, of course, they are neighbors to each other because that's the same point. 1 and 2, let's suppose they are neighbors because they belong to the same class and they are nearby in the space. And 1 and 3 as well. Now assume 1 and 4 belong to different classes, so here it's going to be 0. They are not going to be nearest neighbors. And the same happens with 5 and 6. Here we're going to have something like this, and here, of course, like this, because points 1, 2, and 3 are nearby each other in our space, and they belong to the same class, the same positive class. The opposite is going to happen with points 4, 5, and 6. They are going to be considered neighbors among themselves, but they are not going to be neighbors of points 1, 2, and 3 just because they belong to different classes. So we're going to have a matrix like this. This is going to be a sparse matrix. As you can see, this is not actually a matrix, but actually a list. So we're going to have this vector in the first element of my list, this in the second, third, fourth, fifth, and sixth. Okay? And of course, this sparse array will contain 1, 1, 1, and here nothing because it's sparse, and every time it happens a 0, nothing will be represented in my list. So at the end, this is the output of this function called equivalence relation. I'm going to clean up, of course, because this is like almost the official code. And next, what I'm going to do is the space compression. So I'm going to call this function compress space. This function compress space takes this. This are list, as I told you before, containing points from 1 to 6 and their vicinity in terms of points 1 to 6. What is going to happen is exactly this. All those points, they are nearest neighbors. I'm going to consider something easier here for now, 0 here. So all those points, they are nearest neighbors, they will be compressed. into a single column and a single row. So at the end, all those three guys are going to be represented by, so points 1, 2, 3 will be represented as a single point in my space. The same is going to happen with points 4, 5, and 6. So I will have a matrix like this, 1, 2, 3, and here 4, 5, and 6. And here I'll have something like this. Those are nearest neighbors among themselves, and here 0, they are not. Here 0, and here 1. That's my reduction. That's what this function compressed space does. It's going to tell me that instead of having 6 points in my space, I can represent that using 2 homogeneous regions, 2 homogeneous class regions, because all those points belong, for example, to the positive class and all those to the negative class, for example. And as they can be connected in terms of equivalence relations, you can just think that as open balls whose radius allows me to connect points belonging to the same class. That's what's happening inside this. So all this function is exactly about reducing my space to homogeneous regions, okay? Space regions. At the end, I will have a matrix, actually a list M. And that list M will be used inside this code here. Estimate the number of hyperplanes. What I do here is exactly this. I will take advantage. I can explain this actually just telling you step by step, but it's easier if I tell you like this. If you call this function estimate number of hyperplanes, you're gonna give your input space, your class labels, and here, as you can see, I will compute the equivalence relations in terms of open balls whose radius are defined inside this function as we've seen before. And here we're going to compress the space. After compressing the space, this will tell me how many, this list will tell me how many homogeneous class regions we have in our input space. From that, I compute the lower bound for the number of hyperplanes we need according to the results. Let me add here, according to the results, the theoretical results by Harpeld and Jones. Okay. Of course, this is going to compute the minimal number of hyperplanes we need to shatter our space, and this the largest number, the greatest number, okay, to divide our space. So this will be like, for example, 5 hyperplanes are necessary at least, and at most 7 hyperplanes, okay? So I will add up that in a given matrix F that I'm building up here. What is this for about? This is going to increase the sample size, adding up more elements in my analysis. For example, you can see I start with 10 elements. Suppose you give me the iris data set. What I will do, I will basically take 10 elements of the iris data set, as you can see here, and consider only those 10 elements. Oh, but they could belong just to a single class, to the same class. You can see here that I randomized all examples. So I randomized assigned those to X and assigned labels to Y, so I can perform some random subsampling over here. So I am subselecting, for example, 10 elements, analyzing the equivalence relations, compressing the space into homogeneous class regions, computing the number of hyperplanes I need for 10 input space points. What happens next? I will increment this from 10 to the number of elements I have in X. And that depends on this parameter length. If this is 20, of course, I'm going to go from 10 to a given number, creating in this sequence 20 values. For example, if this is like 200, for example, I'll have 10 as my first analysis, then it will be 10 plus something. Of course, I can compute like this sequence from 10 to 200, whose length is equal to 20. So I will start analyzing using 10 points, then 20, then 30, then 40, then 50, all random subsampled from my X and my Y, analyzing how they can be connected to each other. That's what an equivalence relation is. And then compressing the space to get homogeneous class regions and computing the number of hyperplanes, the minimal number and the maximal number of hyperplanes I should use. Those numbers will be returned at the end, but there is something else. I also compute this linear regression. This linear regression is actually a regression in between the number, take a look here, the number of homogeneous class regions. Actually, in this matrix F, I am concatenating along the rows the number of elements I am subselecting, the number of homogeneous classes found in that space, the lower number, the smallest number of hyperplanes I need, and the largest number of hyperplanes I need. What is the result here? You can see I give some names for this variable f, for the column. So the first column is going to be referred to as n, or the sample size. This will be the number of homogeneous regions. So this will contain how many regions we have for that particular reduction, whose initial value was like 10, and after reduction, let's suppose it's like 2. The minimal number of hyperplanes, big omega, and the greatest number of hyperplanes, the largest number of hyperplanes, big O. So I use this reduced, I try to compute a linear regression using n as input and reduced as output. What is my objective in this particular regression? Is to obtain what is the possible reduction we have here. For example, let's suppose for some space with 100 elements, we could reduce it to 10 homogeneous regions. Then for 200, we reduce to 20. Then for 300, okay, 300, we reduced that to 30. What this means, I will perform the linear regression and obtain, of course, some slope for my line, for my linear regression, that's going to be equal to 0.1. What that means? That means basically that as I increase the number of examples in my sample, I have the possibility of mixing 10% of the elements. So 10% of the elements belong to class overlapping regions, to regions of my space in which elements from one class mix or are somehow overlapped with elements belonging to a different class. That's really interesting because, of course, if this is 0, let's suppose it's going to be like this. This is going to be 5, and here 5, and 5 forever. So the slope is going to be 0. What happens if the slope is 0? I know there is no class overlapping. I know my space has no class overlapping. That means I can perform the bestest possible classification in my space. If my slope is like 0.1, it means the maximum accuracy I can obtain is something around 0.9. Why? Because 1 is the maximum accuracy and 0.1 refers to the points belonging to overlapping regions, to class overlapping regions. So this subtraction gives me my expectation in terms of accuracy, and that's really, really interesting. Let me clean up. Okay. Besides that, we also have this function, estimate shattering. Estimate shattering is going to compute for us what is the shattering. Actually, it's going to bring some estimation for the shattering coefficient, for the lower bound and the upper bound of the shattering coefficient functions. Actually, you can read the parameters, everything, but at the end, I will provide the results found using estimate the number of hyperplanes for this function, and then it will compute a lower bound and an upper bound for our shattering coefficient function. What happens here is basically an estimation for our shattering function, just an estimative, okay, of our shattering function. It's going to be plotted at the end, but it's just an estimation. What is more interesting is probably what happens inside this function, complexity analysis. This is much more interesting. What happens here, and I want you guys to take a look, is you can provide to this function an input space in form of a matrix, as you can see here, using iris dataset and the class labels here. What we're going to do here is we're going to produce a final report, as I told you in the previous video. We're going to run the estimation of the number of hyperplanes we need, okay, for this data set, and also the estimation of the shattering coefficient function. Then I take advantage of a package called, let me remember, I think the package is called R-Markdown. This is a package that helps us to render a PDF file. So it's going to produce a PDF file for us. That PDF file will contain all the information that is here. That information is exactly what I told you in the previous video. So this will generate a PDF report for you guys, which is a very interesting report on the number of examples we need to ensure the training sample size and, of course, all the details after the statistical learning theory. Guys, I hope this is enough for you. Take a look on this paper if you have like any doubt. That's a paper I shared with you in the previous video as well. This is a paper that describes all this package in details, okay? And just drop by now in my office hours to discuss, to bring your point of view, and of course, to ask questions. Thank you, guys.